In this lesson, we'll learn how to determine whether or not a molecule is polarity. We've already discussed the fact that in order to describe the properties of a particular compound, we need to be able to determine its polarity. In order to do this, we need to use some of the skills we've previously learned, such as drawing 3D molecules and determining bond polarity in order to help us. So we already know how to determine if a bond is polar. And a bond is polar when the difference in electronegativity between the two atoms is between 0.5 and 1.7. Now, just because a molecule has polar bonds, it does not necessarily mean that the actual molecule is polar. Let's look at an example. If you draw the molecule of CO2 from the Lewis structure and then to the 3D diagram, you'll see that there are two double bonds between carbon and oxygen. If we look at the difference in electronegativity between carbon and oxygen, we see that it's 0.89. So the polarity of this bond exists between carbon and oxygen. Oxygen has the greater electronegativity, so that means that the dipole in this bond will go towards the oxygen. So in this molecule there are two dipoles going from the carbon to the outer oxygen. Now dipoles are like little vectors, and so when we want to look at the overall polarity of a molecule, we need to add the vectors within that molecule. So as you can see, there's a vector pulling this way, and there's a vector pulling this way. And these vectors are equal and opposite, and will actually cancel one another out. So this is an example of a molecule that is nonpolar, despite the fact that it has polar bonds within it. Any symmetrical molecule will exhibit this. So if you look at other geometries like trigonal planar geometries, even though it might not look like it at first glance, if there are dipoles pulling equal and opposite in all directions in a trigonal planar molecule, these dipoles, when added together as vectors, they will cancel one another out. And this would be similar for something like a tetrahedral geometry. In 3 dimensions, the vectors, if they are all going equal and opposite, they'll cancel one another out. So it's much like if I walked 5 paces one way and then walked 5 paces the other way, my starting position hasn't changed from my final position. Now in this course, we don't need to physically be able to add the vectors, but if you are in physics, then you know that in order to add vectors, it's a tip-to-tail addition. So this vector would add to this vector, and we'd get this resulting vector. So you can kind of see that those ones can cancel one another out. All you need to be able to do is recognize when the dipoles will actually cancel one another out. So if you want to decide the polarity of a molecule, you need to start by drawing the correct molecule using the Vesper theory. Then you're going to look for lone pairs. If there are lone pairs on the central atom, that's usually going to end up with a molecule that is polar. Let's look at an example. If I've got a molecule, I won't use any atoms, but if I've got a molecule that has lone pairs on it, the lone pairs themselves are going to be negative. So that's going to lead to a slightly negative charge on this end of the molecule, leaving this end of the molecule more positive. And that's what a polar molecule is. It's a molecule that has some kind of slightly negative and slightly positive end to it. It is possible to have a situation where the lone pairs actually cancel one another out, and we'll see an example in a few moments. If there's no lone pair, and the lone pairs don't help you to make a decision, then you're going to do what we did above, and you're going to draw appropriate dipoles on the polar bonds. and decide whether or not the dipoles cancel. The best thing to do is for us to look at some examples. So let's start with CH4. CH4, you take some time to draw the actual molecule. It's tetrahedral. So when we look at this molecule, we see that it's symmetrical. So no matter what the polarity of the bonds, the dipoles, if they existed, would cancel one another out. So that leaves this molecule to be nonpolar. Let's look at CCl4. CCl4, you go through the process, drawing a Lewis structure, and then making decisions about its VSEPR structure. It's also going to be tetrahedral. So a tetrahedral molecule, if all the atoms are the same, doesn't matter if these bonds are polar. The molecule is going to be nonpolar. There's going to be no slightly negative or slightly positive end to this molecule. Let's look at CH3Cl. We're moving through a series of molecules that are similar to one another. They're all tetrahedral in nature, and we're just changing the atoms attached to the central atom. Now this particular molecule is not symmetrical. The atoms attached to the central atom are not the same. So what we need to do is actually look at the difference in electronegativity between the individual bonds to decide if there are polar bonds. The difference in electronegativity for CH is 0.35, leaving a non-polar bond. So there is no dipole there. The difference in electronegativity for CCl is 0.61, leaving a dipole on this particular bond. Once we've labeled the dipoles on the molecule, we can see that this dipole will not cancel with anything else. So that's going to leave this particular molecule slightly negative at this end and slightly positive at the other side. So this molecule is polar. XeF4 is square planar. So 2 lone pairs on the xenon with the 4 fluorines attached. So when you're following the steps to deciding polarity, you'll stop at the second step here and look at the lone pairs. If there was just one lone pair, that would leave this end of the molecule slightly more negative than this end. But because we've got the 2 lone pairs, they essentially cancel one another out, much like dipoles would cancel each other out. At the same token, if this is a polar bond, this dipole would cancel with this one, and this dipole would cancel with this one. So overall, this molecule is also going to be nonpolar. Now, IF5 is square-based pyramid, so it's also got an octahedral geometry, and it's got 1 lone pair on it. When we go through the process here, this lone pair has nothing to cancel with it. So this is going to be a polar molecule. I don't need to study it any further than that. I don't need to identify whether or not the bonds are polar in here, because this lone pair is going to result in, overall, some kind of polarity in the molecule. The biggest thing that I can emphasize here is that it's really important to take the time to draw the proper 3D molecule before making any decisions on polarity.